Welcome to this explainer. I gotta tell you, I am absolutely thrilled you're here today because we're looking at what is easily one of the wildest, most mind-bending mathematical facts I've ever come across. Literally, it's gonna change how you look at the hidden patterns of the universe. We're starting with basic physics and ending up somewhere totally unexpected with the pi collision paradox.
So think about this for a second. What do sliding blocks have to do with circles? Right off the bat, you'd probably say, absolutely nothing. Blocks have straight, rigid edges. They move in straight lines. Circles are, well, they're circular. You wouldn't really expect the math of one to dictate the physics of the other. But what if I told you that straight-line physics secretly hides the universe's most famous circular constant? Okay, let's dive into this and see exactly how that's possible.
Section 1. The perfect collision setup. To really get to the bottom of this mystery, we first need to lay down the ground rules for our little physical thought experiment. We're going to strip away all the messy, complicated stuff of the real world. Just picture an infinite, perfectly frictionless plane. On the left side, we build a massive, immovable wall. And then we just place two sliding blocks on this frictionless floor. That's the whole shebang. A flat surface, a wall, and two blocks. Sounds pretty innocent, right? But for the math to work out perfectly, we have to make one big idealized assumption. We're dealing with perfectly elastic collisions. Basically, when these blocks smack into each other, or into the wall, zero energy gets lost to heat or sound. Momentum is just fully 100% transferred. Those are the strict rules of this universe we've built. No friction, no energy loss, just pure momentum bouncing back and forth.
Section 2. 3 simple bounces. Okay, so for our very first trial, let's make both of these sliding blocks weigh exactly 1 kilogram. Let's call the block coming in from the right block A, and the one just sitting between it and the wall block B. So, step 1. Our 1 kilogram block A comes sliding in and smacks right into our 1 kilogram block B. Because they're the exact same mass, block A transfers all of its momentum and stops dead in its tracks, sending block B shooting toward the wall. Then, step 2, block B hits that immovable wall and bounces right back. And finally, step 3, block B catches up to block A, hits it, transfers its momentum back, and sends block A sliding off to the right forever. Block B is now perfectly still and block A is gliding away. And we're done. For this incredibly simple one-to-one example, we get exactly 3 total collisions. Block A hitting block B hitting the wall, and block B hitting block A one last time. 3 bounces, and the whole system is perfectly resolved. Nothing too crazy yet, right? Section 3. Increasing the mass. But what happens when that first block, block A, gets way heavier? Let's bump its mass up to 100 kilograms, while leaving the smaller one at just 1 kilogram. Now, when that 100-kilogram giant hits the tiny 1-kilogram block, it doesn't just stop. No way, it's way too massive for that. It keeps plowing forward toward the wall. That poor 1-kilogram block gets caught in the middle, ricocheting back and forth like a pinball between the immovable wall and this incoming giant. It transfers momentum over and over in this rapid-fire sequence of bounces, basically trying to push against the larger block's momentum to force it to turn around. As you can guess, it takes a serious amount of physical work for that little block to reverse the big guy's direction. But eventually, it actually does. And when the dust settles, the math works out so beautifully. We end up with exactly 31 collisions. A 100-kilogram block results in exactly 31 total bounces before both blocks are safely gliding away to the right. Well, let's not stop there. Let's push this thought experiment to the absolute extreme. What if we take the mass of the big block and multiply it by another power of 100? Let's compare our 100-kilogram block to a massive 10,000-kilogram block. That tiny 1-kilogram block is going to have to bounce against the wall a staggering number of times to push back a 10,000-kilogram behemoth. Let's trace the data here. When the big block was 1 kilogram, we had 3 collisions. When we increased the mass by a power of 100, making it 100 kilograms, we had 31 collisions. And when we increased it by another power of 100, making it 10,000 kilograms, well, if you calculate the idealizing assumptions exactly, the total number is 314 collisions. Let those numbers just sit in your mind for a second. 3, 31, 314. You see the pattern forming here, don't you? Section 4, the pi phenomenon. 3, 1.4, 1.15, 9. That's right. As you keep increasing the mass of that big block by powers of 100, from 1 to 100 to 1,000 to 1,000,000, the total number of collisions perfectly matches the starting digits of pi. I mean, how wild is that? But why does this happen? Well, it's not magic, it's actually geometry. If you were to mathematically plot the kinetic energy and momentum of these two blocks on a graph, the resulting equation actually forms a perfect circle. So every time the blocks collide, you move a specific distance along the edge of that mathematical circle. By multiplying the mass by 100, you're effectively shrinking the angle between each collision by a factor of 10. You are literally calculating pi in base 10, digit by digit, through elastic bounces. To quote the source material directly here, quote, "The digits in the number of collisions will always match the starting digits of pi." Think about that. This isn't just some quirky little trick for the first few numbers. It holds true to infinity. By simply counting the exact number of elastic bounces on a frictionless plane, you are fundamentally computing pi.
It is just absolutely astonishing. We started with sliding squares moving strictly back and forth in straight lines, and somehow the mathematical fingerprint of a circle emerged out of nowhere. So I'll leave you with this question to chew on. If pi is hiding right here, literally embedded in the mechanics of straight-line collisions, where else in the universe is it waiting to be found? It really makes you wonder about the underlying architecture of reality, doesn't it? Thanks so much for joining me on this explainer today. I hope this blew your mind as much as it blew mine. Keep questioning, keep learning, and I'll catch you next time.